So there are many categories of wasps. My favorite are the solitary wasps, and of them, the digger wasps. The digger wasps dig a lot, sometimes. Several feet into the ground they can dig. They're careful and they're smart and they're precise. The fossorial wasp, for instance, she will go out looking for crickets, paralyze them, drag them back home, and so it can be a long way. You have to go up, like climb up a tree, fly down, because the cricket's heavy, and have to go up another tree. It's a mission. But when she gets back to the hole, she has a little ritual. She takes the cricket, drags it to the edge of the hole, right on the edge, goes down, checks things out, comes back up and grabs the cricket, then drags him down to the depths where she lays her eggs, stores the cricket, comes back up, seals up the hole. Are you still following me? And then, so when, like the puppy wasps or whatever they're called emerge, they have some food. It's a pretty good system, but a long time ago, someone found a bug in it. Hey. Wasps aren't bugs. I guess crickets are. The ritual goes like this. You drag the cricket to the edge of the hole. You go down, check things out. Come back up and drag the cricket in and go lay some eggs. But for some reason, some weird person found a flaw or a hack. If you messed with one of the steps, you could get the wasp into an infinite loop. After dragging the cricket to the edge, while it was down checking things out, for some reason, I don't know why, moved the food just a little bit. Just a little bit. It was like a couple of inches. And when the wasp came back up, she was like, this is not right. So she dragged the food to the edge of the hole, then went down to check things out, and the dude moved the food. And then it's like, what? So she dragged the cricket to the edge of the hole for infinity, which, I mean, it was like in 1800, so infinity was only about 40, but then they just gave up, they got bored. That's how you defined infinity. It was just like, no, I'm not doing this anymore. I read that on a Snapple lid. Today, I want to talk about rendering things, and with the intention of rendering stuff for the web and stuff for our applications, widgets and user interface components. And I want to look at doing them with what, I mean, I don't think it's a real term, this functional rendering, but that's what I'm going to call it. So I want to look at rendering things, functionally rendering things, and then doing that in React and React Native, with the goal to making some cool widgets. So I want to start with pure functions. The wasp going into infinite loop was not a bug, it was a feature, like all of our bugs. It's a feature, not a flaw. Wasps have a big problem with parasites. So while she's out looking for crickets, flies and stuff could get in to the nest, into the hole, and if she didn't go down and check it out, then the flies would eat her eggs and things, and it wouldn't be good. When she comes back up and the food has moved even just a bit, she'd have to assume, damn parasites, better go down and check it out. The wasp was a pure function, from cricket to puppy wasps, an array of puppy wasps. No messing around with the state. Always got to come back to the same inputs, same outputs. Even if someone sits there forever, we end up with our puppy wasps. So looking at some examples of functions and a test for you guys. Here's an example. What is the result of this expression? I was doing a little bit tricky there with the DVD icon in the middle. Oh, yeah. Damn Unicode. Okay, 7, thanks to the DVD. The point is it's always 7. Every time you run this, nothing's ever going to change the fact that it's 7. Well, unless they ever change Unicode. But how about this guy? What's the result of this one? Sign starts at the bottom and cos starts at the top. It's 1. Okay, cool. Here's a trickier one. I have a function that takes an x and returns x times x. And what is the result of square 1.5? I put 0.5 because I thought that was pretty nasty. I don't know if... I looked it up on my calculator. 2.25. Anyone? 2.25. Are you sure? You really sure? Yes. There's no reason that this function will never not return 2.25. What does it mean if it didn't return 2.25? It would mean like the apocalypse and the computers were topsy-turvy and dogs and cats living together. What about this guy? Anyone? No, I don't know. And we see this more of an example of an impure function which is relying on some sort of hidden state. I've got a function of omega which takes an x and returns x times app.ratio. ratio. And what's the result? Come on. They told us in school, like anything multiplied by 0 is 0. Functions like with side effects or that rely on hidden state are dangerous, can be dangerous. That's where pure functions have some really nice qualities. They make it easier to reason about the behavior of our code, to make like assumptions about the behavior, what optimizations we could make and things like that. They're composable, and I want composable to sort of run through this talk as a theme, I guess. If we know what has to go in and we know what comes out, then we can use the output as the input of something else, and we know that it's not going to break anything else, then we can use all the functions together, and they'll always work for all eternity or until the apocalypse. But I want to talk about rendering and specifically making like widgets for the web and stuff, which is harder to do without side effects thanks to the technology we have. It's hard to do anyway because the easiest way to think of a drawing API is through some functions that let you draw some stuff on the screen. So here's an example where I'm calling the same function twice. It should draw the same rectangle. I'm trying same inputs. I should get the same outputs. But it's relying on a whole bunch of context. That's why it's context. So depending on the context, we'll get a different output. Additionally, Canvas is a bit slow for making widgets. You can do it. But pushing pixels is pretty slow. Using the built-in effects, then you get the built-in shadows and things, which we'd get with CSS. So we want to be able to do some more interesting stuff. So WebGL, that's an option now because it's supported everywhere. And it's really fast, and we can, make 3D games that are really amazing. But it's old, and it's a big ball of state. Here's some boilerplate for setting up something just to draw a couple of triangles in WebGL. And of the boilerplate, these bits set global state. It's a mess. Like you can feel that it's an old API when you use it. You can feel the parts that are troublesome. And you have to be careful because you need to put things into a state, do the drawing you want, change the state, do the drawing you want, and then it becomes hard to reason about what is in that the next frame of rendering. So if we were going to go with something that had no state and was just pure functions, well, how could we draw anything then? Haskell guys if you ever do your intro to Haskell, then you know this problem. It's like, you can't change anything, you can't change state, what am I supposed to do anything? There is a way in the browser that currently exists, and I don't know much about it, but it is one. It's the CSS-only drawing thing. I don't know too much about this. I like it, because what I like about it is it's declarative, it's stateless. But I don't know if you'd want to use it. It looks pretty hairy underneath. But it is one option, but I don't really want to go making my widgets this way. So I want to know what some other options are. And I want them to be really fast because I want to do a lot of pixel pushing and a lot of advanced effects. So I'm going to revisit WebGL. This is the WebGL pipeline. It's all the steps that happen to get some code from the API, goes through a rendering pipeline, and there's a couple of places where we're allowed to mess with stuff before it gets drawn to the screen. And this happens every frame. So it sets up the pipeline, and you can mess with it. There's two places in here. There's a vertex shader, which is for defining your geometry and your vertexes in space, and what things are going to sort of have a shape. And then there's a fragment shader. They're the orange boxes in this. The vertex shader defines the geometry in 3D. So, I mean, it's not in 3D, the model is 3D. It could be 4D or 2D, it's just a model, but it gets projected onto a 2D screen, and usually it's 3D because that's the one we like looking at. But if you draw it on the screen, then it just looks like this. It's just a mash of color because screen is 2D. We don't really have 3D screens. The way that we get some 3D effects and things that look like 3D is through the fragment shader. And the fragment shader is what's responsible for doing all the lighting and fog and highlights and things like that make things look really cool. I don't know why there was a hashtag in there, I'm sorry. The way that the fragment shader works, so you have your geometry and it's made up of triangles. So whatever your shape is made up of a whole ton of triangles. And for each triangle, one of the steps in that render pipeline is the vertex shader. And this is where we have a chance to color things in. The first example I showed where it was just flat, we're just choosing a color white. For every pixel, we're saying this is the color, it's white. Here I'm saying it's red, so I don't know if you can really see it there. Every pixel is red because I'm setting the fragment color to be 1, 0, 0, and 1 for alpha. That little bit of snippet of code is GLSL, GL shader language. It's kind of a C-like language. It's pretty interesting. It has some interesting properties that we'll look at in a minute. And the thing that makes it so interesting is that although the WebGL whole API is very stateful and you need to be careful where you're mutating things and changing things, shaders themselves are very functional. They're just a function from point to color. And so for every spot on a triangle, you get to choose what color comes out. It'll say like the first pixel, and you say it's red. The second pixel, and you say it's red. The third pixel, you say it's slightly less red, and then it looks like we have shading. Or, of course, just like CSS drawing, which is kind of, seems like a hack, a cool one, people do abuse them, and instead of just making lighting effects, people start doing Winamp visualizations. Because they look really cool, and that's what we want. But this is all in the browser now, and it's all supported in a lot of places, and we can use it everywhere. So there's this sort of a side stream of shader coding that's sprung up in the world, and it relies not on the geometry and 3D shapes, but it's just on two triangles. So here's my phone on the side. And the two triangles are a box. And we know from the web, we know the box model, we know things are made up of boxes. But we can convert every box into 2 triangles, and we have a box. And then for every pixel on the screen, we can run a program. Think about that, that's pretty crazy. For every point, we get to run a program and say what color should come out. And like everything on the internet in the world, as soon as someone comes up with like a little creative idea for using something, it goes out of control. Here's some video from this year's Shader Showdown Finals, which is live coding GLSL shaders in competitive mode. That's from the revision demo party this year. And people make, if you look on shadertoy.com and GLSL.heroku.com, there's amazing amount of effects and creative output from simple, tiny functions. And that's what the shaders are. They're made up of they're just simple functions that are pure and can be composed. And once you have those 2 properties, you mash things together and you can make something bigger and you can rely on that. And that's when things get interesting. So this is just a little aside. Just like in the CSS shaders, the CSS drawing, you can start making extra shapes. People figure out, hey, if I can run a program at every dot and I figure out how far each point is from the center of the canvas, and I make it either black if it's further away or red if it's closer to this point, then I have a circle. And so you have a simple thing for making a circle. And then that extends to other shapes, simple functions that generate a shape. Then they can be combined because it's just a function, and you have things like the minimum function. I'll show you this guy. Here's an example. They've defined a box, which was one of those previous functions, and a cylinder, and then the minimum from the surface to whichever one is furthest away gets drawn, and they looks like they intersect. Looks like there's the union of the 2. And you can do the opposite and get the intersection, and then you can start carving out shapes. And then you can have more complex shapes that are just made up of these same small functions added together. And again, it's the internet, so people go crazy. This is from a PC demo, a 64K. It's a 64K demo, but this is just one tiny piece of it. There's a lot in there, all made up of those functions together, composed. And you're making these scenes that are crazy. That's the power of pure functions and composability. And that's what we need to start. That's what I'm really interested in. There's something at the moment that, okay, let's get out from shaders and 3D and things, and we'll go back to web dev a bit and apps. There is a technology that's becoming big now that is kind of following this idea of composable pieces and in a functional manner, and that is React. It's a JavaScript library for building user interfaces. But everyone, when they first heard it, was like, oh, no, not another framework. But this one, I love I love the core ideas of React, which is this idea of composability and pure functions. And now, how is React a pure function? Well, you make up your components, and whatever you want to get, because it has this one-way data flow model, to get anything into a component, it has to come from above a parent or be part of its local state. So there are 2 ways that you can affect how something's rendered in React, which means it's a function of its properties passed down and its local state, which is only looking after itself, to their virtual DOM thing, which then under the hood gets turned into real DOM, which I think is not the interesting part of React. This is the interesting part of React. You get the benefits of pure functions like being able to reason about it and being able to do performance optimizations, all the good things that we come from the shaders, that come from pure functions. In case you haven't seen it, here's a terrible example I just quickly wrote up, but you'll have a component, you can pass in some properties, and inside the components you have the state. So then your app becomes a composition of these components. And like I said, it isolates the state in the component and then can be composed, which is what I'm talking about as being interesting. Whew. So now, finally, I talked about shaders, and you guys were all like, whoa, those shaders are really cool, Earle. And then I talked about React, and you were like, yeah, React, that's really cool now. So obviously at this point, you're all thinking, can't we have React and shaders together? Well, I've got some good news. Introducing GL React. This is a project that we've been working on at our super secret startup. It's a little bit less super secret now. It's called Project September. I can say the name. We've been working for the last 5 or so months on an application that will be out in January. It's all React Native and GraphQL and fun stuff. And the business is in the social fashion, something like that. Now, the problem with this is that it needs to look, it's not a problem, it's an excellent problem. If you're going to release a fashion social app, it has to look really cool and it has to be really interesting. It has to get people quickly. You have a small time to try to get somebody hooked on your app and go, and it's, fashion, they're fickle, So our designer, she's really good, and she wanted a bunch of things that just don't exist as designers want. And so we decided it was a good chance to get the power of WebGL into our React Native app. It seemed to make sense, and thanks to my good friend and co-worker Gaetan Ronaldo, who came over from Paris 1 week, the first week he started with us, and churned out most of GL React. Now he's made it awesomer, and I'm presenting it. GL React is the 2 triangles I talked about before. 2 triangles make up a box. The box is the component. So in React, whatever you would be rendering is these 2 triangles come out. Because it's WebGL, it's super fast, and you can do some interesting things. Because it's React, and because of the way we've written it, it's very composable, and you can, instead of having one-off little shaders that I was showing you before, you have the ability to compose the shaders in a React way and make complex effects, which you can then package together as a new effect and use that somewhere else and package that together as a new effect, and all those advantages of composability can be yours. What can it do, Earle, you ask?
What can it
do? He asks. Yes, sir. Well, it can do, I said it's 2 triangles and shaders. So it can do shaders, just like I was showing you before. Like, that is what it does. It can draw 2 triangles. You can run a GLSL program for every pixel in those 2 triangles, and you can do fancy shader effects. But that's not why we built it. We built it because we needed it for making widgets and making things that we couldn't do in the UI alone, in DOM. So, for example, we needed a way to Instagramify things. We needed a way to rotate hues and change text dynamically. We needed to draw things. And now this one, I like this one because it's using, where's it going? It's using, where's he go? He's not going. Anyway, it's a pie chart. It doesn't look, it's a pie loader. It looks better than that in real life. There we go. Now it's using that idea of drawing a function. Where am I at this point? If the pixel's here, am I on or off? That kind of thing. So it's using all the same techniques that come from the crazy demo scene world to draw a UI component that's going to be in a fashion app. That's kind of cool. I like that idea. It can do more advanced things. Here's, you can't really see it on here, but it's like instant tilt shift with vignette effects, and you start composing. It's very snazzy. But where can I use it, you're asking?
Where can you use it?
Hey! Everywhere! Well, country and Western, iOS and Android, and desktop. So it's a good library for doing some cool things, but just like React, I think the important things are not like what fancy pants things can it do, is what are the core principles behind it, and what I think is most interesting about this, and I've said it a million times now, is the composability aspect of it. Being able to know that what you're putting in is what you're going to get out all the time, and being able to take the output, put it as the input of something else, and make something bigger. Where am I? And it gets rid of all the crappy WebGL stuff, which is really nice because the WebGL stuff is horrible. So today, actually, or maybe tomorrow, is the launch of GL React version 2. Way! You don't have to clap. You didn't even know GL React version 1. No, our first version of it was kind of a prototype, and now this version is much more powerful and works as a React component, as a DOM, as React Native, and in the DOM, it's hitting WebGL in the browser, and it's hitting, we had to write a bunch of Objective-C and Java for React Native, so you guys didn't have to. The API is pretty simple, and in fact, it got a little more complicated in version 2 to take advantage of this, what I've been banging on about, composability. I'll quickly show you how this is getting the simplest shader you can into our GL create shader, which is exactly modeled on the stylesheet.create from React. We make a component which is a function that will render out a GL node, which is the part in the middle, and the GL node is the effect itself, the thing that you want to do. So here I'm saying it's that hello GL effect. And it can take some extra things that I'll talk about in a minute. Now the final part, and the reason that the API is like more verbose on this end, is because we've split out the surface. Now the surface is what finally renders it. So there's a surface for React Native, and there's a surface for the DOM. And the effect goes in the middle. What's good about that is that the effect in the middle is now, it doesn't care where it's running at all, and it remains exactly the same everywhere, and you can package it up and put it on NPM, and anybody can use it in React Native or wherever React goes next, and it will work, like by magic. I'm going to skip over this one. You can rasterize a bunch of stuff, like images and other GL nodes, so I'll talk about it in a minute. Here's an example with React Canvas, spitting out some images and text that get turned into Canvas, which then you can run your pixel shaders over, your fragment shaders over. Okay, finally, my favorite thing is composability. This is where I think that it's a really cool tool. We start with a dog with a garlic clove on its head and whatever. You make before I showed the create component, and it spits back, it runs the GL node, and will affect whatever the children are. So here, I've made that just a plain old React component, which is the blur, and it can then be used with whatever you put in the middle, either a URL or another GL node, or another GL component. And then you can combine them. So then you make another one. Here's the hue rotate effect, and then our dog's gone blurry and funny colored. And then you can combine it with a negative effect, and then it's gone blurry and hue rotated and negative. And what's output is then another effect that you can have an effect called blurry rotate negative thing, and then use that anywhere inside your programs, which is really cool. Also, because it works like React Native, like React, it lets us do some other crazy things. Like the most impressive is being able to share nodes. We make a render tree, like an AST that is what needs to be rendered. Then we can look at things for referential transparency, say that's the same thing, that's the same thing. They can be the same node, and we can do a bunch less processing in WebGL, which is really interesting. And as I said, then you can just package them up as your effect that you want run, my effect. And anybody in the world can use them. In fact, just today, there has been 6 effects pushed to NPM, so you can start playing with them today. GL, React Negative, and contrast saturation, and things like that. So we're hoping that this is going to grow and people are going to start adding really cool effects. And the beauty is that none of the power of GLSL is hidden from you. If you want to get your hands dirty and be the shader coders competition next year, then start now. It's a good way to start learning. And if you don't want to see GLSL in your life, then go to NPM and find the effects other people are doing, and then you can just apply them to any set of 2 triangles, any component in your app. Lastly is there's the GL React Playground, which will show you your shader broken down into its render tree on the right there, and all the pieces, all the tree that's being processed, so you can see performance issues or how long things are taking and what things look like at each step. Then you can tweak it, and you can make really cool effects. So there you go. Composability is powerful. Try not to mutate state if you can avoid it. And WebGL is going to be really cool for making widgets. Thank you.